People always think we're attacking NASA, and we're actually NASA enthusiasts when it comes right down to it, right? We're space enthusiasts. We want accountability. We want disclosure. We want to see what's actually there, and we will accept the limitations. We'll support the limitations on what's capable of doing. We don't need to keep researching in and find out, oh, all we're looking at is CGI. If you can't do it, say so. This is Bill DeMoss. Bill's going to be giving us a lesson on vacuum.
Thank you for inviting me. I have been really enjoying your content. You've been doing a favor to the whole world because we know how all this silencing has been going on, and I have been enjoying a lot your content. Thank you for all this. If I can help in the slightest, I'll be very happy. Thank you for inviting me.
Bill, we'd like to know for the viewers that watch our channel a little bit about yourself, where you're working at, and the type of work you're doing.
Why do we do vacuum stuff in physics? Because we use it for depositions. If you are to do material science, you may be doing a lot of years in theory, you know, what are semiconductors are, and what are conduction, valence bands, energy gaps, and all that. But when it all boils down to making your first thin film, once you do make it, then you can proceed with all that nice realm of, electronics. All the solar cells, all the LEDs, all the computer processors are made using depositions. Now, why do we use vacuums? It's because if you remember from high school, the definition for something being hot is how fast the atoms are moving inside that material. So if you imagine that down here on the Earth's crust, on the Earth, we are in the bottom of an ocean of air. We have a lot of molecules between 2 points, 1 centimeter, and we do have a lot of molecules. So if we evaporate something, for example, let's say copper or silicon, and we want to make a thin film of it on a substrate on top, then when the atoms come out, their energy will be impacted every time they hit an atom, and by the time they reach the substrate, they will be totally cold. So what we do is we do use a vacuum, and we pump out all the atoms. So from what you're melting to what your substrate, you have no atoms in between. So as something evaporates, it hits the substrate with the same temperature, and so it's still liquid. And then when it hits a substrate, it thermalizes there and becomes a solid there. So vacuum techniques have been very crucial to us. It's very crucial. It's not something an everyday person sees. And that's, I think, where NASA was counting on, that not many people in the 60s and the 70s, and even heck now, even the 20s, we don't have vacuum chambers, lying around. So I saw the vacuum that you used, and good that you did that, because I have also seen the document that NASA has, on their testing, and it's a joke.
I have the original from 1965 film, and I was just reading through more portions of it again as far as what a film can capture in the moon's lighting thing, and it just said the shadows would be absolutely dark. Their test results said that their vacuum tests had no effect on the film whatsoever. And of course, we're already getting at a 10 to the minus 3. And they said the way to protect the film from radiation is to freeze it down to minus 196 degrees Fahrenheit. And of course, you would no way you're going to be able to transport this film because it's just going to shatter like glass.
But it's going to blow it up, I think, if we put in the vacuum, because when we are talking about vacuum, how big of a force can a vacuum be? Well, since we are on this Earth, we are experiencing 1 atmosphere pressure that equates to 101,000 pascals per square meter. If you translate from pascals to force, to kilograms, to a force that most of the people equate to, it equates to exactly 10 tons, 10,000 kilos. If you translate that to pounds, It translates to 22,000 pounds per square meter. It's a lot of pressure. That's why when we build our chambers, the walls are stainless steel, and depending on its size, the walls get bigger. But even in the one that we have at the university, it's 30 centimeters wide. The wall is half a centimeter thick of stainless steel. Because we are dealing with so big forces. One way I deal with physics, because I've done physics as my third degree. My first is in computer science, then I did electronics and hardware design, and then I did physics. What I do with physics is, because it's a synthetic, the way that computer science is, it's synthetic, it's all synthetic, we made it. So if we do have a problem, we are the ones responsible for it. Physics is an analytical approach. Nothing says nothing more than the experiment itself. We may be hypothesizing a lot of stuff, but until we see it down, nothing else matters. So what I'm proposing is, I do have a proper vacuum with a proper equipment. We do have a turbo pump. We can routinely go down to the 10 to minus 6 to the minus 7. Do you have two films, one being a reference and the other being the one that we are going to put in the vacuum? And let's commence with the experiments. I think you did them a favor putting a vacuum as low as 10 to the minus 3. That's basically nothing. From 10 to the minus 6 upwards, everything starts degassing. Everything starts degassing. Rubber degasses, even stainless steel degasses a little bit in the beginning, with the oxygen molecules being inserted crystal lattice. We heat it up so that it spits out the atoms from there as well. But structurally, at least, stainless steel can hold. But rubbers and rubber gaskets are useless in that kind of vacuums.
So if we're looking at, say, the Apollo spacesuits, and they have rubber seals in them, and they're well beyond 10 to the minus 6. When they're on the moon, they're at 10 to the minus 11.
Yeah, do you know how much pressure he should be losing? I've seen it. It is a joke. They're using like zippers. You can't even use zippers for a very low vacuum, not a hard vacuum like that. Imagine that, if you have a small hole in your vacuum chamber, sometimes this happens because of manufacturing small defect. You get to the machinist is not so happy that day, or it's a Monday or whatever. So within the welding, you do get a tiny pinhole, not even visible by the eye. And the way we trace them is we pull the vacuum, and then we go around the chamber with either soap water or another gas that is different to air, and we try to see what makes a difference in the vacuum. It's a bit hard to find those holes because they don't even show up. They are not even visible. When we are talking about seeing the holes visibly with the eyes, it is a joke. Ask any physics guys, and if anyone tells you otherwise, it's just they are afraid of the dictators, of the current status quo. If you say something that goes against the message, then they try to pull you away.
One of the things that the comments that we get when we're talking about vacuum is we have people stating that it's not actually a force.
A vacuum is a lack of atoms, okay? It's an emptiness. But when you do get atoms together, they start hitting each other because they have a thermal energy. And because of that, they start taking up space. If you try to compress something and the molecules inside are whizzing, they're hitting the walls every time. And those walls, since they're also thermally quite hot as well, so you do get something that cannot really be compressed. The more molecules you put inside, the more molecules are hitting the walls every time. You get a pressure, you get a force when you get a difference. If you put a small box of 1 square meter of a face, if we take a wall of 1 square meter, and on one side we put 1 atmosphere, and on the other side we put a vacuum, the pressure there is gonna be 10,000 kilos. The whole pressure. That thing has to withstand 10 tons. So you can extrapolate from there how much of a joke it seems to be that they had a whole LEM, however big it was more than a 1 meter square meter, and having a 1 millimeter thick of aluminum wall.
But here I have a question for you, Bill. What happens is some of the subscribers or people that watch our show, what they'll also ask is that, well, space is already a natural vacuum. No work had to be put into that process of removing the atmosphere. The vacuum was already there by nature. But when we take something and we want to test it like you do, like when you're testing semiconductors in these vacuums that are torr 10 to the minus 67, what happens is now there's work being done to remove that air. And they're saying that there's a big difference between that and what you're seeing in space. Are these substrates going to react the same?
Vacuum is a vacuum wherever you are. We do need some work to make a vacuum here because we are in the bottom of an ocean of air. If you have a bucket and you have it filled with something, you have to use some work to evacuate it. Yes, it's not in the gravity world that we are within the Earth. So of course, yes, you don't need any work. You already are outside of the gravity. You've done all that work. Or you haven't fallen into the Earth's atmosphere anyhow. What they don't tell you is that the work we put is the work that was needed if we have some air. Out in space, of course, it would be scattered around. Atoms, would automatically scatter around because they have no pressure to hold them together. But if you take that atom and you start putting it into the Earth's atmosphere, it would like to go there because it's less energy. It's losing energy. Well, we cannot produce as much of a vacuum here because it's very, very hard, but it's as close as it can be.
But then what about the spacesuits now? See, we come to that, and we come to rubber seals. When you supposedly get to torr 10 to the minus 6, the rubber seals are no longer viable because they will outgas. So then what is holding these suits together in a vacuum that is said to be on the lunar surface of torr 10 to the minus 11 to 12? So my question is why aren't these seals outgassing? Are they some special type of a rubber or special material? What's with that?
What's holding them together is fantasy.
It's just like we were saying this morning. NASA stands for the National Animation Simulations Agency.
Remember the video that was put up talking about the spacewalk on the ISS, and he had a 2-centimeter hole punched through his glove by a micrometeor? Can you imagine punching a hole in a glove with a micrometeor and not damaging his hand? And then he worked outside, out in the spacewalk, for 10 hours or more. And he said it was a little red mark on his hand from the vacuum. I mean, he'd be dead in seconds.
It was a white lie. They were trying to go against the Russians. They were trying to show that they had good power to go against anything that Russia threw against them. Okay, it was a white lie. That's not to end up in a war. Nobody died. Generally, it was a good white lie for what its purpose was. However, having seen that, so much money is so easily taken away from the taxpayers, well, they are following with the same scenario. And now, ESA, the European Space Agency, is also following step. A lot of projects are boxed and held in storages in Brussels, for example. So, yeah, it's a nice way to money launder. You are doing a favor, actually, to the American people. The whole world knows. The whole world and laughs. If you show the photographs of, the LEM having landed on the solar soil with no hole underneath, or the zippers, anything from the whole expedition to a physics person privately, he'll start laughing. All the students that I had 300 students in physics. 300. Nobody will believe this fantasy.
I really appreciate what you said about that, Bill, because it seems so obvious when you examine it. I mean, any scientist, any physicist, anybody who understands what vacuum is and what vacuum can do, it's not rocket science. Vacuum is a very straightforward, simple examination. Take the air away and something happens. Why do you think people haven't commented on this before?
We are going through a war. Did you see 4 years ago how every content that was against the main narrative disappeared?
Yeah.
They're actively fighting you guys. Not only you. You know, a lot of people are saying out the truth. It's when it goes against the narrative. It's the new order. It's the new way to tackle things. We don't like them, eradicate them.
Yeah.
A very big money grabber. Even now, ESA, the European Space Agency, is following the same steps. But NASA started it. NASA showed the way. You give the people enough happiness, you know, it's like, there's some goal. It's a nice way to chew up their money.
Yeah, but it's a monetary industry, just like everything else. Like even Christmas is just that. When you were a little boy and your parents sat down and said, there is no Santa Claus, but there was still a present from Santa under the tree, wasn't there? Well, that's what NASA should be doing. No, we really can't do it, but we're giving you this. We're indulging in your imagination, right? And that's why they are building these monstrous movie studios.
You know what, the guys that are now there in NASA, the young scientists, they have nothing done faulty. They don't deserve the sins of their predecessors. Why is it so hard to come clean? Because the whole world knows. If they came clean, the whole world would gain some trust back in them. Now the whole world, of course, has lost trust in NASA and the medical industry, the way Bill Gates got tangled into the game, and a lot of other players. So, yeah, it's easy for the people to lose trust. That is the beginning of the end for a lot of stuff, and they do not realize that this is the beginning for them of their ending, because there has never for the world more connected and more brains being together thinking with the same goal. Their time is limited. It is a joke. We have a saying in Greece, ο κόσμος το έχει τούμπανο, the whole world knows, και αυτοί and them, κρυφό καμάρι, hidden pride.
I think I was the first person to identify this as a problem 5 or 6 years ago. That lecture I attended by Phil Pressel, who was talking about the camera system on the Hexagon spy satellite, which he's very proud of, and quite rightly too. What I didn't know at the time was that the Hexagon camera systems had only been declassified a few years earlier. I mean, we're talking 2012 when the camera system was declassified. He gave the talk, which I heard in 2018 in London, and it was an offhand remark he made during the talk, which was to the effect that, well, we had to keep the film under pressure. And I thought, why is that? And basically it was if the film wasn't under pressure, it wouldn't work. So I asked him afterwards, I said, look, would the same requirements be necessary for Apollo to keep the film under pressure? He said, of course they would. Film is film. Film is damaged in a vacuum. And that was where the whole thing started. Well, it started for me. I don't know if anybody else has picked it up. And it was as a result of that, and talking about it, that I realized that this is actually a major problem. It's nothing conspiratorial. It's nothing silly like that. It's science. If you put material into a vacuum, it has an effect. The vacuum has an effect on that material, as you've described. It'll outgas. It'll cold melt. Those are the two major problems with vacuum. If those things happen, and they will, because science cannot be denied, if the science is correct that materials outgas in a vacuum, photographic film outgasses in a vacuum, photographic film is destroyed, as Robert has already demonstrated, by using 10 to the minus 3, which is a relatively low vacuum. It's not very much. You start putting it into some of the equipment you've got, film would be completely destroyed, and you couldn't even get into a camera.
It's going to be video recorded in the vacuum chamber. Bill's going to do that for us. As the vacuum is being pulled down, the gauge will be there to be seen. You'll see what the level is on it, and you'll physically watch this film. It's going to curl up. It's going to off-gas out of there. I don't think you'd be able to take the film and be able to load it in a camera.
As Marcus said, physics is the same everywhere. So, yes, we are going to see it firsthand. I'm gonna put the film in. I'm gonna film the whole procedure, from beginning to the end. And we are going to be also putting some film, not in a canister, but really on its own, to see what it does structurally, because I do think it's going to start bloating up. I'm hypothesizing here, but I think it's going to start bloating up. That would be an eyesore for NASA. I'll be very happy to send you the video when we get the films. I'll be very happy because it's sorted out.
Marcus, he's going to be putting batteries in there, and we're going to see what happens.
The battery, all the electrolyte will evaporate. Yeah. It will get very cold in the process, but it will eventually evaporate. And, of course, you will lose your battery, because the battery is just two different metals in either a base or an acid.
Well, then that takes out the rover, doesn't it? The batteries that were on the rover would be history, outgassed, gone.
If the batteries in the rover were their own vacuum chamber, then they would have been all right. But they are not. They were not fortified.
Well, the LEM's the same way. They depressurize and open the door.
Bill, what is the lowest or the hardest vacuum you can pull in your chamber?
We go to the 10 to minus 7. We could go lower, but we do need some preparation. We need to bake the vacuum chamber. I think the 10 to the minus 6 to the minus 7 is plenty enough.
I would think so.
How badly it goes under that vacuum, well, we can only extrapolate from then onwards for the 10 to the minus 11, till it destroyed at 10 to the minus 6.
If it's in the chamber at 10 to the minus 6, and we see what it does then, you can then extrapolate from that on to 10 to the minus 11 and 12.
Yeah, Marcus, if it's totally destroyed at 10 to the minus 6, what else can you do to 10 to the minus 11?
Well, you see, there should be no change at 10 to the minus 3. And we're already getting a change in the film at that level. Yeah. I mean, you're just going to accelerate that by 100 times or 1,000 times, right?
What I did with the film's negative is I put that outside of a microwave oven. I poked 2 chopsticks in to the door switches so that it would stay on. And then I took the roll of film and I put it just outside the door and I gave it a 1-second burst. You want to see what happened to that film? It just wrecked it. And I understand that's a 2 gig magnetron that we're talking about, and it's not cosmic rays or anything like that, and it's concentrated, of course, but still, you'd think that it wouldn't have that much of an effect with the door open and it just being right by the door, crack of the door, but it did. So my question is, what is all this harsh cosmic radiation and these CMEs like we're seeing that came off of the sun when Artemis was supposedly out there? What's that going to do to the electronics? If they had any film that was on there, I mean, that's what they use in a nuclear power plant. They have film in the badges. The same thing with airliners, stewardesses, the pilots. They have film in those little badges. So what is this going to do to the film when you get out there beyond the Van Allen belts and you have all this cosmic radiation flying at you at the speed of light? What is that going to do to the film?
Robert, we are again doing them a favor, as you say, because if we put it only under vacuum, we are not putting it under radiation as well. And also, we are not thermally stressing it. If you see, NASA was stressing supposedly, when they were doing the tests, they were going from minus almost to 150 degrees Celsius with the film. Now, if you raise something, and you raise its temperature and you bring it up to 70, 80, 90, you greatly increase everything, all the processes. So if we are to be very harsh, not only we should put it in a vacuum, but we should heat it up as well. And that way, not only it would degas like crazy, it would be in an accelerated manner, doing that. If it were to survive, like 2 days with a bit of heat, it's going to survive 2 hours.
When I did one of the experiments, I used a heat lamp and I put a gauge inside of the vacuum chamber and I brought it up to 150 Celsius.
Oh, good.
And I wanted to see what happened to that film. The film curled up, but then the NASA proponents come along and they say, well, you cheated because you used a heat lamp. Well, what's happening when they have those cameras outside on the CSM? There's cameras, there's film cameras on there with 1,500 feet of film on that camera roll. So what is that doing to the camera, especially when those astronauts were orbiting above the moon and they had to stop the barbecue roll to take the pictures of the lunar surface? So that means that those guys were in the sun being heated up like a Christmas turkey.
The only way to lose energy is through radiation. There's no convection. There's no air to come to you and take away the heat. So yes, they would be boiling. They would be boiling, but the film would be boiling as well. And Marcus and Robert and you, Scott, you've all seen film. We have all seen film. Was anybody not expecting that outcome? 150 degrees. If you left the film in the car in the summer, not at 150. So yes, one at a time, I think. We'll put it simply in a vacuum, and then we will also heat it up in the vacuum as a different experiment.
Yeah.
To show that there is no possible way, even taking away the extra parameters, the extra, evil stuff, there is no way.
And then we go back to vacuum in these spacesuits. So how can they test these spacesuits for that which they're going to be finding on the moon or encountering on the moon, on the lunar surface, when it's said to be torr 10 to the minus 11, and yet their vacuum chamber only goes down to torr 10 to the minus 6 to 7. The one in Sandusky is the one that goes down to minus 6 to 7, but they did not ever once put a spacesuit in that chamber to test it. They only put the spacesuits in that one chamber that can only go down to minus 3 to 4. That's it. That's all they tested it to. And they heated it up. And I have video of photographs and video of them heating it up with heating elements. I think everybody's seen it. I mean, I've showed it many times on other shows. But you think that would have even started the outgassing faster, wouldn't it, of that material on those spacesuits?
Bill, maybe you could explain for the people that watch our videos the relationship between temperature on molecules, how they're excited, and vacuum.
Okay, the temperature, the thing it does, it energizes the molecules. They start whizzing about faster. When you start whizzing around faster and you hit a wall, you hit it with a bigger of a force. Yeah. So if the molecules being balls flying around in space, and you're trying to put them in a confined area, the more you're trying to confine them, the more they push against, because they're going like crazy.
So they create heat at that point, when you're compressing them.
They have heat because they are moving already. Everything that is above zero, the absolute zero, even at absolute zero you have a slight kind of, you have quantum fluctuations. But when you start heating things up, the molecules there start moving around. That's how you get pressure. You heat something up and those things start moving inside. And they're hitting the walls. If you make it colder, it will start, those molecules will become slower and they will be hitting the walls lighter, in a lighter manner. The thing can collapse easier on itself. If it's a balloon, yeah? If it's a balloon, the forces that make the walls are greater than what the molecules are trying to pull apart themselves. If you heat it up, it's going to grow a bit, because you give energy to the atoms and they start moving around faster, and they're hitting the walls in a kind of more serious way. So they keeping the balloon more expanded.
So if you take a material, let's say we just use water as an example,
okay,
right? So we have the atmospheric pressure holding water together, and when you get up to 70,000 feet, it no longer can hold together.
Okay, let me tell you what happens. Imagine you are an atom, a water molecule, okay, and you're going around. If I start increasing the temperature in the liquid, those molecules are starting to travel around faster. If I increase it more, some become so kinetically energetic that they can break free and they can become liberated and become a vapor atom. The pressure is holding the water together. If you start losing the pressure, if you start going higher and higher, then the barrier gets easier to escape from the liquid state. It gets easier. Nothing is confining you in your blob, it's easier for you to just jump out.
You're increasing the evaporation as you drop the pressure down.
Yes. You're increasing the evaporation, and if you got a blob of water, let's say we now put it to the 10 to the minus 3, not only it will start, evaporating, it will furiously start evaporating. It will start boiling. That's evaporating and making bubbles.
So that's the relationship between temperature and vacuum.
The vacuum is a lack of any atoms.